Welcome to Brain Vision.
In this problem, on the topic of conservation of energy, we are told that a bead is sliding without friction around a loop, as we can see in the figure. It's released from a rest at a height h, which is given as 3.5 times r, where r is the radius of the loop, and we want to calculate its speed at point A, as well as the normal force on the bead at point A if we know the mass of the bead. So for part A, if we look at a diagram, the speed at the top can be found from the conservation of energy for the bead track Earth system, and the normal force can be found from Newton's second law. Now we'll define the bottom of the loop as the zero level for the gravitational potential energy. So we know the initial energy of the bead, EI, is equal to its initial kinetic energy. So this is its initial mechanical energy. That's its initial kinetic energy plus its initial gravitational potential energy, Ki plus Ui. But it starts from rest, so its initial kinetic energy is 0, since its initial velocity is 0, and its initial gravitational potential energy is mg times h, which you can write as m times g times 3.5 r. So we've written the initial energy in terms of r. Now the total energy at point A, we'll call it EA, is equal to its kinetic energy at this point plus its gravitational potential energy, Ka plus Ua. So that's a half mVa squared, where Va is the speed of the bead at point A, plus its gravitational potential energy, which is mg times 2r, twice the radius of the loop. Now, we know that mechanical energy is conserved, and so we can equate the energies at these 2 points. So that means the initial energy at the top must equal the energy at point A, EA. So let's equate the two expressions, and we get m times g times 3.5r is equal to a half mVa squared plus mg into 2r. So we can rearrange and simplify, and we can solve for the speed at point A, which you want, and we get Va squared is equal to 3 times g r, the acceleration to gravity times the radius of the loop, which means that Va is equal to the square root of 3 times g times r. And so we can calculate the speed of the bead at point A, provided we know the radius of the loop. And that's our answer for part A. Now for part B, we want to find the normal force, or the magnitude of the normal force at point A, if the mass of the bead is 5 grams. Now to find the normal force at the top, we'll construct a force diagram as we've done here. We can see that the normal force acts vertically downward from the top of the loop on the bead, and the weight of the bead also acts vertically downward. So we use Newton's second law, and we take the sum of all the forces in the vertical or y direction, and this must equal to MAY, where M is the mass of the bead and AY is the y component of its acceleration. So the normal force N plus the magnitude of the weight mg must equal to mv squared over r for the centripetal motion of the bead. So this means that the normal force N is equal to m into v squared over r minus g, where capital R is the radius of the loop. And we can write this as m, and we know an expression for the speed, which is 3 times gr. Since it's all squared, the square root side vanishes, divided by r minus g. And this gives us the normal force to be 2 times mg, so 2 times the weight of the bead. So this is 2 times the mass of the bead, which is 5 grams, or 5 times 10 to the minus 3 kg, times the acceleration due to gravity, 9.8 meters per square second. So calculating, we get a value for the normal force on the bead at point A to be 0.098 newtons, and that's vertically downward.